I know word problems can sometimes be a little bit daunting, so I've given us a 6-step process that we can use here for our applied optimization problems. We're going to draw a picture, take some notes, define our variables. Then we're going to find a formula for what we want to maximize or minimize. That formula we're going to need in step 3 to get down to one variable so that we can take its derivative in step 4 so we can find the critical points of our function. Step 5, we're going to use that new second derivative test to determine whether we're looking at a maximum or a minimum. Make sure we don't accidentally get the wrong one. And then the last step is to just answer the question that was asked. Sometimes we get a little bit lost working on the problem. We'll go back and double check to make sure we're answering the question. And it's a word problem. We will always put units on our answers. I'm going to do one more example for us today. If you go to the resources for the week and click on the Campbell's Soup GeoGebra applet link there, that will bring you to this page. And Tim Brzezinski, the author of this applet, measured a Campbell's cream of chicken soup and found its height and circumference. And from that was able to calculate that the surface area, the amount of metal used to make the can, is about 44 square inches. If you scroll down on the page a little bit, you'll come to a cylinder there. That's our can of soup, which doesn't look a whole lot like a can of soup right now, and a corresponding graph. So on the graph, what he's doing here is he's holding that surface area, that amount of metal constant at 43.8325, about 44 square inches. He's holding that constant, and he's allowing us to pick the radius of the can. And so we're going to try to figure out which radius choice gives us the maximum amount of soup, the maximum volume of that can. So on the horizontal axis of the graph is the radius and then the corresponding volume. And we can see that there's a spot there where the volume maxes out. And you can just kind of drag this around. So right now the radius is about 0.7893. And then as I make the radius bigger, because we're holding the surface area constant, that height has to shrink so that we can use the metal to make the can wider, so it has to get shorter. And of course, there's the sweet spot. If we make the can like ridiculous over here, kind of like a can of tuna now, we made the can really wide, so it has to get very short. All right, so we're going to try to figure out for the amount of metal that they have to make the can, what's the maximum amount of soup or volume that we could fit inside the can. So of course, we're not going to rely on the applet alone to give us the answer to this question. What's the maximum volume we can get using 44 square inches of metal to make a can? All right, and so I have some helpful formulas there. We're going to have the volume of a cylinder and the surface area of a cylinder. And I always make a promise to my students when we're doing applied optimization problems. I will never require you to know a formula that we haven't already used in an example, either in videos, in Zoom class, or in a homework problem. All right, so as you go, if there are formulas like this that you don't know, just take note of them and put them on your cheat sheet for the exam. All right, so we have that 44 square inches of metal. That's our surface area, and that's given by 2 pi r squared plus 2 pi rh. So that is equal to the 44. What we're trying to do is maximize the volume. Okay, so this is the thing we want to maximize. And just for good note-taking purposes, the R in both of these formulas is the radius of the can. That's like from the center of the can to the edge. So that's the R. And the H is the height of the can. All right, so we want to maximize the volume, that pi r squared h. That's the formula we want to take the derivative of and find the critical points of. But right now it's got an r squared and an h. We need to get that down to one variable. And we're going to do that using our surface area information. So I need to take this formula right here, that surface area formula, and solve it for one of the variables. And you can choose either variable. Solving that equation for r would be difficult because that equation has both an r and an r squared, but it's only got one h. And so I'm going to solve this equation for h. So I'm going to start off by subtracting 2 pi r squared from both sides, which leaves me with 2 pi rh equals 44 minus 2 pi r squared. And then I'm going to divide both sides by 2 pi r. All right, and this looks sort of terrible, right? That h is equal to 44 minus 2 pi r squared over 2 pi r. Eventually, we are going to do a little bit of simplification, but I'm not going to do it yet. You can't just go crossing out the 2 in the pi just yet. All right, so the whole reason I solved for h is because this value for h, this expression, is the same h that's in my volume formula. So I'm going to rewrite my volume formula by plugging in that value of h. Okay, so my volume formula, so I'm going to have volume, let's just call that V, is pi r squared times that thing I just got when I solved for h, which was 44 minus 2 pi r squared over 2 pi r. All right, and that's not very pretty to look at, but it is down to one variable. Before I try to take the derivative of that, I'm definitely going to do some simplification. All right, here's our volume formula from the previous slide. I'm going to simplify this a little bit. I'm going to think of that pi r squared on the outside. That's a fraction over 1. So since it's multiplying by the fraction in the parentheses, I can cancel some stuff on top and on bottom. So I can cancel out the pi here with the pi down there. And I can also cancel out one of the r's. So this is r squared, and I can cancel that out with the r down on the bottom. Okay, so what I have now is r times 44 minus 2 pi r squared over 2. All right, so you might notice that I've got 44 and 2 pi r squared in the numerator up there. Both of those are divisible by 2, so I can kind of distribute this 2 division by 2 to both of those terms. So I'm going to be able to simplify out that denominator. So I've got an r times 44 divided by 2 is 22. And then the 2 is going to cancel out with the 2 in the right-hand term, and I'll just have pi r squared. And then now I can distribute my r, and we're actually going to have a pretty simple formula for our volume function. And I'm even going to write this as function notation as I distribute that r, 22r minus pi r cubed. All right, so that's our volume function. We want to maximize volume, so we want to find critical points of our volume function. So I'm going to take my derivative, take the derivative of v prime of r. Derivative of 22r will just be 22. And then we'll take the derivative of pi r cubed. Pi is a constant, goes along for the ride. We're going to bring down that 3 out in front and subtract 1 from the exponent. And this is the thing that we're going to set equal to 0 to find our critical points. All right, so let's see. I'm going to add 3 pi r squared to both sides. And that just makes my 3 pi r squared turn positive over there on the right. And so let's see what we've got. Over on the left, I'll have 22 equals 3 pi r squared. Let's solve for r. We're going to divide both sides by 3 pi. And that leaves me with r squared equals 22 over 3 pi. And we'll take a square root on both sides. Now, normally when I take the square root of both sides, I put a plus or minus on there. I'm solving for r. Remember that r is the radius of a can. It doesn't make any sense to have a negative radius. So the positive one is the only one that's meaningful here. So I'm going to get r is equal to the square root of 22 over 3 pi. Now, if you're building a can, you're not going to tell somebody to make it as a radius of square root of 22 over 3 pi. Nobody knows how big that number is. So let's go into our calculator and figure out what this is. So I'm going to divide 22 divided by 3 pi. And then take the square root of that. And I get 1.5278 and change. All right, so let's round that off at a few decimal places. We'll say 1.53 inches. All right, so 1.53 inches. And that's our critical point, and that's probably the radius that we want for our answer. We just want to make sure that we've actually maximized the volume of the can and haven't accidentally minimized it. All right, so we do that, remember, with the second derivative test. All right, so our second derivative test says to figure out whether we are concave down or concave up at our critical point. If it's concave down, that's good news because then we found a maximum. If it's concave up, we've accidentally found a way to minimize the volume in our can of soup, which is no good. All right, so let's see. Let's copy down our first derivative. So our first derivative was 22 minus 3 pi r squared. So our second derivative, see, derivative of 22 will be 0, and then we'll get minus 6 pi r as our derivative of minus 3 pi r squared. And we just want to figure out, is the second derivative of our critical point, which was 1.53, is that positive or negative? So I'm going to do negative 6 pi times 1.53, and then figure out what that is. Of course, it's going to be a negative number, but let's just figure out what it is to write it down. So negative 6 pi times 1.53 gives me about negative 28.8. And I don't care that it's negative 28.8 so much as I care that that's a negative number. And that means that at this critical point, I'm concave down, which means we found a maximum, which is what we wanted. We wanted the radius that was going to give us the maximum volume. All right, so 1.53 inches is the magic radius. Let's make sure that that actually answers the question. So let me go back to the original problem. And it says, what is the maximum volume? They didn't ask for the radius, they actually asked for the volume. So let's remember that our volume formula, let's see, let's use the volume formula that we figured out over there. Okay, so that's our volume formula that just depends on R. Let's plug in our R value for that. So we're going to say our max volume is going to equal V of 1.53, which is 22 times 1.53 minus pi times 1.53 cubed. Again, I'm going to ask my calculator to do that for me. So 22 times 1.53 minus pi times 1.53 cubed. And I get 22.4. Okay, so where am I going to put this? Let's put this up in the top right-hand corner. 22.4, that's a volume. So volume is measured in distance cubed, so it's going to be inches cubed. It's not usually how we measure volume in a can of soup, but we're going to go with it for calculus. All right, so 22.4 inches cubed. Let's hop back over to the GeoGebra applet and see if it agrees with our answer. Here we are back in the GeoGebra applet. I'm going to drag that point onto the maximum volume spot. Remember, volume was the y-axis, so we're going to go with the maximum y coordinate. And I'm eyeballing this here, but it looks like it's about right there, which looks pretty good. We found 1.53 for our radius and 22.4 is our volume. So that looks like a pretty good answer to me. We'll do a couple more of these applied optimization problems when we get together in class.